Hi there, Year 11. It's Mrs. Bush this time. Last lesson you were looking at discriminants and hope you've had a chance to get a better understanding of that. Today we're now moving on to looking at the graphing of quadratic functions. You would have looked at some graphs last year in Year 10, and what we want to do is build on that and extend further and go into more details. What we just wanted to start off initially is to show you sort of where these quadratic functions come from or where they're related to in the world around us. They're sometimes referred to as conic sections, and that's because we can see we actually come up with a quadratic equation if we take a section of a cone. So if you've got an ice cream cone and a nice sharp knife, you could cut through at this angle, and that shape you made is a quadratic equation. Cones are pretty special because we get all these different curves from the one or two cones. So to get a circle, this one's easy. Obviously, you just cut through the middle to make the circle. An ellipse is if you cut through the whole cone at an angle. Hyperbola is if you get two cones upside down on the point like this one and cut through a bit at the top straight down onto the bottom, you get that hyperbolic shape. And we'll be doing a lot more hyperbolas throughout the course. And obviously, those satellite discs, the parabola shape there, you've seen and you've probably heard of, and you'll be doing more of those. Even in the physics course, you're going to be looking at those in more detail. So that's where we see parabolas in the world around us. So let's go in and recall the things that you knew from last year. So last year you would have known them as a parabola, that's the shape. You know your general forms, we've been looking at that already with the discriminant. So here we've got a graph, and I've started to put some of the terms on here that you'll know. The y-intercept, the vertex, and here are some other terms over on the left-hand side, other things that you would have come across. So maybe pause the video for the moment and look at each of those terms and see if you know what they mean or can identify them on the graph. So pause the video now and have a go at this. All right, how did you go with that? Hopefully you'll be able to come up with x-intercept. So your x-intercept, where it cuts the x-axis. In the course, sometimes we also refer to these as our zeros or roots. So these are all the same thing, just different terms. The term zero comes from the fact that we solve an equation when y equals 0, and that gives us these two solutions for x. Roots, just another term, the root of an equation for the x-intercepts. Concave up and concave down. You may not have come across these. Concave up, again, it will apply, you can imagine some of those physics terms with lenses. Concave up, happy smiley face, and in this case, you will have a minimum at the vertex. Concave down, that's going to lead to a maximum at the vertex. So there's some terminology so that if you want to talk about a parabola, you know the correct terms. In the course, we're going to do quite a few investigations, and the point of these is that we get you to look at graphs, identify patterns, and then come up with a conclusion, as opposed to us just saying, this is what we always see, here's a rule, learn it. We want you to get used to exploring things and looking to see what happens to the graphs. So in the first part of this exploration, this investigation, it's in your textbook, you'll see an icon in your textbook, and if you've got your CD in your laptop at the time, you can click on that icon, so I've got it linked in here, and that will open up the graphing package to do with that investigation. So here in the first case, we've got our x minus 1, x minus 3 factors being multiplied, and that will produce a particular graph. Then you can press down, click down and find some of the other functions. In a moment. This one's not doing it, but you can click down and give you some of the other graphs and plot those up as well. I'll just set them up on the board here. So we've got a whole lot of functions here in this first part. The key thing to note is that we've got a situation where we've got two factors being multiplied. So we call this in the factored form. And you may have another number out the front as well. So the first one we've got graphed here, we could graph up is x minus 1. All right, so let's look at these ones. Each of these graphs we can graph up and set this up on your calculator, and we can see with this graph we get roots or solutions or x-intercepts of 1 and 3. If I look at the next one, it's all the same except we have a 2 at the front in this case. So that's the only difference. So let's see when we graph this one, what do we notice? We come out with the same solutions or the same x-intercepts, the same zeros, but in this case, this graph here, this is our red line. This one, it's not really blue, it's a bit purple, but I don't have a purple pen. So this one is a bit steeper than the first one. But we have the same intercepts. Let's now look at the other graphs. So let me take that one off and let's put this one on. I need to make that one disappear. Now when I put this graph on, we'll take the other one off first. This one I can now join on and we see, oh, that's interesting. We've got the same intercepts happening here, but now it's concave down. And the only difference that we notice is this minus out the front. If I disconnect that one, so you could be doing this all on your calculator and looking and see what happens. Here we've got just one factor, a repeated factor. And we see it's concave up, but we only get one solution, whereas before we had 2. So now here's our one solution, and we only have one factor. So at this point, you can go, well, I wonder what's happening with the next one. If it only looks like there's one factor present here, I wonder if it's going to be the same story, but what effect will the half have? So set that one up on your calculator and let's have a look at that one. So I'll take this one away. It's not wanting to do that. Let's take this one off. And connect this one. And I put a pen all over it. I don't think it gets as happy. So here we go. We're at the same story. We get one solution with one factor. But in this case, with the half, what do you notice has happened? One factor means one solution. But the half now, we we see that this curve here is not as steep. So we can see the number of factors determine the number of x-intercepts, and we can also see, if we look at the actual value, we've got a -1 here. The x-intercept happened at +1 on the graph. Same story with this one. In these, our solutions or x-intercepts were at 1 and 3. So even though it's written as x -1 and x -3 in the factors, the actual solutions are at 1 and 3. So that's what you've got to be careful when you're looking at a graph written, an equation written in factored form. It needs to be written as a minus. If the x-intercept is at a +1, then you write it as x -1. So our conclusions we can draw with this one is that the P and Q are the roots of the solutions, the roots or solutions to the equation. And remember, back at the top, it's when it's written as x minus P and x minus Q. Then P and Q are the solutions, and the A value affects the steepness of the graph. And we'll look at that in more detail later. In the second part of this investigation, we're looking at this graph here, or a different setup of the equation. This one's written as x minus h all squared plus k. And when we come to graph these ones, this is what I've got graphed here, x plus 4 and x plus 3 are graphed. If we look and graph just our y equals x squared, just a plane without any h or k, we see we get our nice normal quadratic equation. Once I introduce a plus 4, what can you see has happened to the equation? We see we've got a shift across. So you could start by pausing the video, work through investigation 2, put all the graphs into your calculator and see what effect adding a number inside the bracket and adding a number outside the bracket, how does that affect the position of the parabola? So if you've had a turn to look at those, let's go through a bit of a summary. We found that if you've got x plus 4, we ended up with a shift of 4 units to the left. So that's what happened with this equation. Then I can only graph 2 at a time, so I'm going to take that one off and put this one on. If I now go get this equation and I get plus 3 to it, what do you notice has happened? This value, the vertex here, has gone up 3 units. And that seems to be corresponding to there. So the plus 3 at the end says get your x, add 4 to it, square it, then add 3. So every value is going up 3 units. So our vertex is now at -4 plus 3. Our vertex for this one, do you remember? That was at 0, 0. And this one, our vertex is at -4, 0. So you've probably looked at some other ones in the investigation, the other equations. What conclusion can you draw? The vertex of the parabola is at HK. So remember, we've written up our general equation as y equals ax minus h. All right, that's very important you see that's written as a minus. Plus k. So the k value here is the same as that, but the h value needs to be seen as minus h. So x plus 4 is like going x minus 4 squared. So that's why our vertex here is at minus 4 and plus 3. So let's do a bit of practice with this one. Here's some more graphs. Let's quickly go through and put in the vertex. So pause your video. Here are some equations. I've already got a couple graphed. See if you can quickly work out the vertex and see what effect do these numbers at the front. Try and have a guess based on what we've looked at already. All right, so which ones have I got graphed up here? That one's graphed and this one. So let's go back to the beginning one. Here's our first one. Hopefully you worked out our vertex is at 3, 2. Because it's written as x minus 3 all squared and plus 2. Our next one, because we still see it at minus 3 and plus 2, then I think it's going to be the same place. What effect do you think the 2 has? Do you remember that from earlier? This is saying 2 times, so we're thinking it might be steeper. So let's graph that one. Yes, that one is steeper. So our 2 is making the graph steeper, but the same vertex. But the 2 says it's steeper. Next thing is, what about our minus 2? What effect does that have? So take that one away. Not going away. Let me shift that out of the road. See if that makes a difference. Right, now we're better. Okay, this one here, let's put this on. What do we notice? Upside down. So if I take, let's shift this. Not wanting to go away. Right, let's leave that one. So the minus 2, we can see it's steep, and it would be just the same as this one up here, just as steep, but it's now upside down. So vertex still at 3, 2. It's steep, steeper than the first one, but it's now, what's the correct term? Concave down. The last one now we're looking at, if we've got this third in here, what are you going to predict? Hopefully you're going to see that the vertex is going to be at the same place, because that's the same. All right, so now I've got it working there. So we've graphed this last one and same vertex, which is great to see, not surprising, but we're now not as steep. So hopefully we're getting some patterns here that are getting repeated each time. What's our conclusion going to be after this part of the investigation? That the A value affects the steepness of the graph. All right, so a quick summary, just to pull everything together for this vertex form. So we had a factored form, we now have a vertex form. For the vertex form, if A is greater than 0, we've got concave up. If A is less than 0, it flips it upside down and it's now concave down. If A is between -1 and +1, that means it's like a fraction, then remember the fraction made it wider, not as steep. So this one here means we've got a fraction, a positive or negative fraction. A equal to 0, well if this was a 0, that just wouldn't make any sense, you'd have no equation. So another way of writing that is with this notation here. So this is using an absolute value or modulus. So you may not have come across that. If you haven't, basically if we take the modulus of a number, it's saying what is its distance from 0. So the modulus of 3, or the absolute value of 3, is 3 because it's 3 units from 0. The absolute value of -3 is also 3 because it's 3 units from 0. So when we write it in this notation, we're saying we want a value for A that's less than 1 unit from 0. So that means we've got all those fractions from -1 to +1 not inclusive. So that's another way of writing that one. So if we've got a fraction, the graph is wider, so it's more spread out, not as steep. The last option here is when we have our value for A that's bigger than a value of 1. So this one here is matching this modulus notation. That's where we're saying A can be bigger than 1 or less than -1. And those are the graphs that we saw get steeper. Concave up if A is positive, concave down if A is negative. The book now goes through a summary of all the different types of equations. So the first one we looked at was in factored form. So a quick summary here. Factored form, P and Q are real numbers. The notation for a real number is that notation. So that means it can be whole numbers, they can be fractions, they could even be irrationals. We could have an equation with x minus y is equal to x minus root 2 x plus root 5. So these can be any real number, positive or negative, fractions, decimals, or irrationals. Remember to get our vertex, then take the average of the two roots and the roots of the x-intercepts. So the x-intercepts of P and Q, axis of symmetry is the average of them. To get the vertex, you want the x value, that's matching this, and then substitute this back into the equation to get the y value. So pause the video, have a go at this equation here, do a quick sketch of it, and write down what are the roots and what is the vertex. All right, hopefully you've had a go at that now. I can look at this equation, x minus 1, x minus 2, tells me my roots are at 1 and 2. 1, 2 on my quick sketch. The vertex, I can tell by taking the average, is going to be 1 plus 2 over 2, which is 3 over 2, 1.5. So I can substitute that back in the equation. So it's going to come through there. To get the y coordinate, I then need to substitute in to get minus 2 times 1.5 minus 1, 1.5 minus 2. So working that out, substituting it back in, we now see our vertex is at 1.5 and 1/2. And that makes sense. If we look at our graph, it's minus 2. What does the minus tell us? Concave down. So our vertex is going to be up here somewhere. This is a rough sketch. So there's our vertex and a half. So our curve is going to be looking at this shape. And then if I want the y-intercept, I need to get -2 times -1 times -2, which gives me +2 -4. So I would now know that this graph will continue and intersect that -4 for the y-intercept. So hopefully you've had a go and be able to sketch that up just from the equation. It's not totally accurate, but it's not too bad. Next one, if we have a graph in this form, it's in factored form, but what do you notice? Only one root, so that means h is a real number, again, and we're going to have it touching the x-axis, so we'll only get one x-intercept, and that intercept is at the vertex. So it touches at h, the axis of symmetry is x equal to h. If they ask you for an equation for the axis of symmetry, it is most important you always write x equals to h. If you do not put the x equals in, you do not get your marks. So that's a hint for exams and assessments. So here's our vertex at h0, depending whether this is positive or negative, determines whether it's concave up or down. So pause your video again for the moment, see if you can do a quick sketch of this graph, find out your x-intercept, which is your vertex axis of symmetry, as well as your y-intercept. Okay, so hopefully you had a go at this one. You've found out that your x-intercept is, or your vertex is at -5, 0. So here's our x-intercept. Axis of symmetry is going to be x equals -5. Very neat writing. There we go, that looks a bit better. So our axis of symmetry is coming down here at x equal to -5. The y-intercept, when x is equal to 0, comes out at 50. So that allows us to put this point up here. We can then put a corresponding symmetry point over here. What would be the coordinate of that one? If this is -5 units, it's a nice symmetrical function. So this value here will also be -5. So this point here is going to be at -10 and then 50 for the y. So you can always come up with 3 points for your equation. So a rough curve, you need to get used to drawing your parabolas and make sure that your vertex is a nice curve, not a point. Next one here is where we're into the vertex form of your equation. So a quick review of this one, vertex form. So this is where HK is our vertex. Axis of symmetry will be at x equal to h. Vertex, it's being translated. This is a vector way of describing the translation. This is the first time you've seen this, and we're going to be looking at this a lot more in later chapters and when the topic of vectors. This is saying that it's like a coordinate, but it's describing how a function's being moved. So the h refers to the movement in the x direction, and the k is referring to the movement in the y direction. That's my abbreviation for direction, because it's a long word to write out, it doesn't fit in. So that means for this graph here, for this function, example, if I've got 5 and -15, remember it's set up as a minus, so our vertex is at 5 and -15 for the vertex. So that means compared to just getting a normal x squared function, there's been a translation of 5 units in the x direction and minus 15 in the y. So if I could just get a normal quadratic like that, then I can move it 5 units to the right. So this would be 5. And then minus 15 in the y. So that's what that's meaning. So we're now down at minus 15. Then we can work out the vertex. We've got that already. Axis of symmetry is at x equal to 5. The y-intercept, we're going to get, remember, when x is equal to 0, we'll see how if my graph lines up or not. Minus 5 squared minus 15 equals 25 minus 15 equals 10. So my graph is not quite right because this, well, I can do a fudge factor here. One advantage of smart boards. I can shift that down because my y-intercept here should have been at 10, not at 0 where it was before. So yeah, one advantage, I can shift that around, whereas you can't as easily. So there we are, we can draw up our graph. X-intercepts. How do we get our x-intercepts? Do you remember to get how to get your x-intercepts? You're solving y equals 0. Alright, so when you solve y equal to 0 into our equation, then solve that for x, bit of algebra, which hopefully should be easy for you, and we come up with our two solutions at 5 plus root 15, 5 minus root 15. Obviously, this is our 5 plus root 15, and this must be our 5 minus root 15. So this gap here, guess what, is root 15. All right, so that one's a quick summary of our vertex form. Last one was our quadratic equation, that you did a lot with that the other day with your discriminant. So this works for any equation when it's written in our general form, ax squared plus bx plus c. Here are our two roots. When our discriminant is 0, that gives us our vertex. The y-intercept is at c. Axis of symmetry we've talked about. If our discriminant is 0 or positive, then we can come out with our x-intercepts, where our discriminant is b squared minus 4ac. Obviously, remember, if our discriminant is less than 0, we don't get any x-intercepts. All right, here's the equation. Have a go at that quickly. Put that into your quadratic equation and come out with your roots. I've got the graph up there already for us. The minus 3 should be telling us why it's concave down. Try again with that. So the negative 3 makes that concave down. So pause the video, have a go using quadratic formula and see what roots you come up with. All right, so you put your equation into your quadratic formula, minus b plus or minus the square root of b squared minus 4ac all over 2a. Go through, come out with what we call an exact solution. You need to know the difference between an exact solution involving our square roots and a rounded solution using your calculator. GDC, your graphic display calculator, and remember 3 significant figures is the standard for your IB papers. So you come up with your two solutions. That's what your graph looks like. And here, this one must be our -4 minus 2 root of 7 over -3. And we have distinct irrational solutions in this case. All right, did that. Okay. In 1C.2, so that was all C.1, so that's a massive amount. In C.2, we look at graphing quadratic equations by completing the square. All right, you're doing really well. This is a massive topic, but it's a big part, and quadratics will come up often in lots of different areas, so if you can get a good understanding of it, it's really important. So, graphing quadratic equations by completing the square. The aim of this is to get it into that vertex form, and some of you will have done completing the square in year 10, but now's your chance to go through it again and make sure you can do it. It is important that you can all complete the square. So what we're aiming to do is to come up with an equation that's looking like y equal to something or other squared plus some other number. All right, so that's the goal, where we're trying to head to. So if we look at this, we can look at this equation as x squared plus 6x, and I put the plus 7 over here, and think, what have I got to do adding here so that I can come up with x something rather squared? So the way to do that is, I think, what's in a normal square, this has been doubled. So if you look at your 6, you're going, what I need to do is divide it by 2 and then square it. So half of plus 6 is plus 3. Then I want to do plus 3 squared. And that will enable me to write down x plus 3 squared. So we know that x squared plus 6x plus 9, there's our plus 9, is the same as x plus 3 squared. But I've added this plus 3. I can't just add something to an equation because it changes it. So if I add something, then I need to subtract it away as well. So if I've added plus 3, I now minus our plus 3, our 3 squared, and that will leave the equation the same. So this first part, x plus 3 all squared, is the first part of our equation. Now I've got to think I want plus 7 minus 9. So the minus 9 is taking away what I just added to it. So our equation is x plus 3 squared minus 2. And if you expanded that, you would get back to the original equation, this one here. So now it's in a nice way where we can draw it because we know the vertex form. So what's our vertex? That's right, it's going to be minus 3 minus 2. So our vertex is going to be minus 3 minus 2. Doing a quick sketch here. So here's our vertex. What else can we know? If we look back to our original equation, our plus 7 is our y-intercept. So we know we've got a y-intercept up here at 7. If I know the y-intercept, I can then make what I call that symmetrical point. So if this is 3 units across here, then I can go another 3 units to get my symmetrical point. So that'll be at minus 6, 7. So now we can draw in our curve through there, down here, and up. I don't know the x-intercepts. We'd need to solve that, and that may or may not happen easily. They may not be rational. From a quick look at the equation, I don't think I can factorise that easily, so they're going to probably be irrational. So our symmetrical point, just so you can write that in, is at minus 6, 7. So now we can do a quick sketch by completing the square. That's nice and simple if the coefficient of our x squared term is a 1. In the next case, our coefficient is not a 1, we actually have a 2 here. So what we need to do is factorise out the 2 to make our perfect square. We want the 2 out the front and the rest inside. So let's have a look at that one. All right, I've done some of the work here for you already. So here's our equation that we're starting with. What we want to do is take out this 2 initially, so it's out the front. So I've taken the 2 out the front, I've factorised it out from just these first 2 terms. I've left the 5 on its own out the back, and we can, because that's going to be part of our vertex. So taking out the 2, I get x squared plus 2x. Now I want to complete the squared, so I need to think, take my coefficient of plus 2, remember I want to halve it and square it. So 2 divided by 2 is 1, and then I want 1 squared. So that's why I've gone plus 1 squared. Remember now, I can't just add something, I need to undo what I just did, I need to take it away. So I need to subtract the plus 1 squared. Let's get some numbers that you can read. But at the beginning of our equation, we've got a times 2. So we're not just adding 1 squared, we're adding 2 lots of the 1 squared. So I'm going to go 2, that looks like adding. Got that again for you. So we're going to subtract 2 lots of the 1 squared. So now we can come up with 2 times x plus 1 all squared. There's our completed square. And now I want plus 5 minus 2 gives us plus 3. So now we've completed the square. Our vertex is at minus 1, 3. And we know from the 2, it's going to be steeper than what would it be normally. So we can sketch that up again. Our vertex at minus 1, 3. Minus 1, 3 is our vertex. 2 means it's concave up. I look at our original equation for our y-intercept. Is at 5. That means I can do my symmetrical point. If this is, what do we have? Minus 1, that's 3. So our symmetrical point is going to be another 1 unit across at minus 2. It's also going to be up at 5 to match our y-intercept. So here we are matching it over here. So now we can do our nice curve through there. Try not to run into our writing. So there's a quick sketch of what this graph would look like. What can you, when you look at that, what can you say about the discriminant for this graph? Do we have any x-intercepts? No. No x-intercepts mean that the discriminant in this case must be less than 0. It's concave up, but no x-intercepts. We've put another example up here where 3 was the common factor. So you could stop the video and look through that one. It's another example. And there's the verdicts we've come up with. So see if you come up with the same answer. So cover that up. Just have a go from scratch. And then we can graph this. And then you do a sketch of your graph. Hopefully it'll look something like that. All right, so there's another example you can do, and you've obviously got more in the textbook for that one. The last section here, 6.3, is again, it's a bit of a repeat, the discriminant of the quadratic. Same verdicts, but we've got different discriminants, and we looked at a similar example to this earlier. So our vertex here, they're doing at 1, 3. But depending whether it's above the x-axis or touching the x-axis or cutting through the x-axis determines the number of roots we've got. So in the first case, no roots. It doesn't cut the x-axis. And you'll probably recall from that that the discriminant must be less than 0 if there are no x-intercepts. Next one, where it touches once, then the discriminant equals 0, and you can do the calculation for that, and you will know that that must be our axis of symmetry at x equal to 1. The last one here, where it cuts twice, that means our discriminant is greater than 0, and we can get the two solutions either from the quadratic formula or factorising. So this is, as I said, just a summary at the end of this section. Quadratic formula, the discriminant's very important. You'll have a lot of questions based on that. Less than 0, equal to 0, greater than 0. The last bit here is just a different term that you probably haven't heard of. It's called positive definite. A positive definite quadratic is where your discriminant is, where A is greater than 0 and the discriminant is less than 0. So that means that, where we are back here, if our discriminant is less than 0, that tells us no roots. If A is less than 0, it means it is, sorry, A is greater than 0, that means it's concave up. And that's why you get a concave up and not cutting through your x-axis, so it's always positive. A negative, let's go, this one shows up. A negative definite means we've got something that's concave down and again a discriminant less than 0. Discriminant less than 0, no roots. And A is negative, so it's concave down. That means an up. So in this case, down, it's down, and no intercepts. So congratulations, you have survived 1C. A long section, lots of information, lots of very important information. So take time, make notes, work out things you don't understand and come and ask for help to go through those in class. Well done.